In this video, we want to talk about how to construct the equation of a plane in 3D, or in 3 space. So remember when we were trying to find the equations of a line in 3 space, all we needed was a point on the line and the direction of that line. And as long as we had those two things, we could, so that was P naught, we came up with our vector equation, r equals r naught plus TV. That was our vector equation of our line L. Well, to come up with the equation of a plane, knowing a point on the plane, P naught, and knowing a vector pointing in some direction is not enough, because as you see, we could make our plane that contains point P, and the vector V here lies on that plane. Or I could make this plane right here that's also parallel, or has a vector on it that's parallel to my vector V and contains P. And actually there are infinitely many planes that contain point P and are parallel to my line, or my vector V. So that's not enough. So what we need, however, if we had a plane, let's draw a plane out here, and we knew a point P naught, let's move that, so we'll say P naught, which has coordinates x naught, y naught, and z naught, so that's this point right here, and we knew a vector that was perpendicular to my plane, we'll call that vector n. That actually is enough to construct the equations of a plane. And let's see why, or let's see how. So let's orient our plane in 3 space. So there's y, there's x, and here's z. And let us draw our position vector to our known point, and we'll call it, as usual, r naught. And let's let P be any other point on the plane. It's going to be our arbitrary point, so x, y, z. And let's let r be the position vector pointing towards my point P. Okay, so those are 2 points that live on my plane. So let's define now the vector between r naught and r. Okay, so this vector right here, which we can call V, but what it's equal to is, r minus r naught. All right, and so this vector V lies on my plane, which contains the point P naught, and I know this vector n here is perpendicular to my plane, which means the dot product between n and V must be equal to 0, right? Remember, the dot product of perpendicular vectors is 0. So what does that mean in terms of my position vectors? So n dotted with r minus r naught is equal to 0. Okay? So this equation right here is called our vector equation of our plane. Now, that's usually not the form that we use when talking about a plane. So we're going to take what we know about r and r naught and n, and we're going to rewrite it into equations that we will use more often. So let's move to a new board. So first, remember, n is our vector that's perpendicular to my plane, which we actually were going to call a normal vector. So that means it's perpendicular to my plane, or orthogonal. All right, and we're going to say it has the components A, B, C. Unlike when we were talking about lines, we used our directional vector V to have the components A, B, C as well. So don't confuse those two. So r is my position vector that points to my arbitrary point on the plane, and r naught is the position vector that points to my known point on the plane. Okay, and what we just discovered on the previous board was that n dotted with r minus r naught is equal to 0. So what is that in terms of this that we have here? Well, that means we're going to take the vector a, b, c, and we're going to dot it with the vector x minus x naught, y minus y naught, and z minus z naught. And we are going to force the conclusion that that equals 0. All right? So, what does that tell us? If we actually perform the dot product, we get a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. And this is the scalar equation. Let me write this up here. The scalar equation of the plane, and the one we will use most often. So it's the scalar equation of the plane through my point p naught, x naught, y naught, z naught, with normal vector n with components a, b, and c. Okay?